Hi, this video will cover section 8.3, the inverse of a square matrix. The objectives for this section will be to verify that two matrices are inverses of each other. Use Gauss-Jordan elimination to find the inverses of matrices, just the same steps as what we did in 8.1 to solve systems. And to use the formula to find the inverses of a 2 by 2 matrices. There's like a special formula, more like a shortcut, I guess. And then for matrices of bigger dimensions, we do have to use Gauss-Jordan. Also to use inverse matrices to solve systems of linear equations. So the inverse of a matrix is a concept that we will have to use because we do not have division with matrices. And so if we have a matrix and we call it matrix A, the product of matrix A with its inverse is going to equal to the identity matrix. So to give you an example with numbers, if we multiply 3 times 1/3, we will get 3/3, which is equal to 1. So the number 1 is considered to be the identity for all real numbers, and so is the identity matrix for all matrices of that same order. Remember, only for square matrices. So the term between 3 and 1/3, they are related because they are reciprocals of each other, but they're also multiplicative inverses. And we do use the word multiplicative because the additive inverse is a completely different thing. The additive inverse, if we have a 3, what do we have to add to a 3 to get a 0? And so that will be -3. So additive inverses are different, and that is because the additive identity is 0. The multiplicative identity is 1. And that is when I talk about numbers, real numbers. When we talk about matrices, we have the identity matrix will be the more like a multiplicative identity, just like 3 and 1/3. So if we have a system of equations, and here let's just assume that A is a real number, like 3, and then A inverse will be the inverse of that number, like 1/3. So to give you an example, and let's just do one with numbers. So let's assume that we have 2x is equal to 6. And so we know that to solve for this equation, we divide by 2 on both sides. But without using the concept of division, we could use the multiplicative inverse of 2, which is 1/2. And we could multiply that 1/2 on the left and right side of the equation, and that is the exact same thing as dividing by 2. Now the 1/2 and the 2 we could actually, I did that wrong. We're going to use 1/2 and 2, and together they make up a 1, and that is what we consider the multiplicative identity. And then we still carry out the variable x, and then on the right side we have 6 over 2. We carry out the multiplication. So at the end we have 6 is equal to 3. Okay, so however, I'm going to, let's do the following. Instead of writing it this way, we will have 1/2 times 6, and we know that 1/2 right here, this one, is going to be the multiplicative inverse of 2. So we could say 2 to the negative 1, just to match the notation from this side, times 6. But you still know it's multiplying by 1/2. And then let's just add that step here. Now we're going to do the same thing, but with matrices. And let's highlight this part here. A inverse, or a to the power negative 1, is the multiplicative inverse. Remember when we were in chapter 3, we went over properties with exponents. If you have a negative exponent, you can put the bring the base, which is the big number, the 2, to the denominator to the power 1, and that will be exactly the same thing. Okay, so let's do the same thing with matrices. So let's say that we have a matrix A, which is the coefficient matrix. Then we have matrix X, capital X, for the unknown variables. And then we have a matrix with the constant terms, the numbers, and that is representing a system of equations. So if we want to solve for that system, what we will have to do is multiply by the inverse of matrix A on both sides, like that. So we have here matrix A times X equals, and then here matrix B. So if we group matrix A inverse times A, we will obtain the identity matrix. And that is the one that has 1s across the main diagonal and 0s everywhere else. And so, oh, and I'm missing matrix X. And here on the right side, we will just have A inverse times matrix B. And so we know that identity matrix times any matrix, it's going to result in the same matrix that we have here. It's like multiplying a number or a variable, like in this case, times 1. And the way that we're going to solve those systems, so instead of solving regular linear equations, we will be solving a system by multiplying the inverse of the coefficient matrix times the constant matrix. So we have here one of the properties that we already went over. So if you multiply a matrix times its own inverse, you will obtain the identity matrix. And remember, A with the negative 1, as it looks like an exponent, it means inverse. Inverse of A, or we can say A inverse. Also important to remember, matrix A, the original, must be n by n, meaning that it is a square matrix. And the identity matrix, it will also be of the same order n by n, order or dimension. So not all matrices have an inverse, but if it exists, then we call it a inverse, and that is the notation for it. So remember, an inverse will be like 2 and 1/2 because they equal 1. In this case, you have the number like the original matrix, and then you have the multiplicative inverse, and if you multiply them together, you obtain the multiplicative identity. So for example 1, we are going to verify or show that B is the inverse of A. So the question here is B equal to A inverse? And this is a question. So the way we're going to verify is by multiplying AB and then times BA. So we're going to do that. And to review multiplication, we take the first row times the first column. And so we start like this, -1 times 1. And then 2 times 1. Oh, and we add it. Then we move on to first row and second column. So this will be -1 times -2. Plus 2 times -1. And then we move on with the second row from the first matrix times the first column of the second matrix. So -1 times 1 plus 1 times 1. And now we're going to multiply the second row of the first matrix times the second column of the second matrix, and that will be -1 times 1 plus, oh, I made a mistake. It should be -1 times -2 plus 1 times -1. Okay, so now we're going to carry out the multiplication and then the addition. So we're going to have here -1 times 1 is -1, and then 2 times 1 is 2. Then second row, second column is -1 times -2, which is +2. 2 times -1 is -2. Then we move on to second row, first column. -1 times 1 is -1. 1 times 1 is +1. And then we move on to second row, second column. So -1 times -2 is +2. And then +1 times -1 is -1. And now the next step will be to multiply. I'm sorry, to add. So -1 plus 2 is 1. 2 minus 2 is a 0. -1 plus 1 is a 0. And 2 minus 1 is a 1. And so that will be the answer. Now let's do the next multiplication, because multiplication with matrices is not commutative. So we need to verify the multiplication in both directions, AB and BA. So if we multiply here, we will have 1 times -1, which is -1, and then -2 times -1, which is +2. Then let's move on with first row, second column. So -1 times 2 is a 2. And then -2 times 1 is a -2. Then we move on to the second row, first column. So +1 times -1 is -1. -1 times -1 is a +1. And then we move on to second row, second column. So 1 times 2 is 2. -1 times +1 is -1. So here we will have -1 plus 2 is 1. 2 minus 2 is 0. -1 plus 1 is 0. And 2 minus 1 is 1. So as you can see, in both cases, we obtain the identity matrix. We have ones across the main diagonal and zeros everywhere else. So in this case, it is true that AB equals BA, and because they both equal the identity matrix. So what we could also say is, instead of calling it matrix B, we could call it A inverse. And so that is how we show by obtaining identity. And this will be a commutative. And so just to remind you, not all matrices have an inverse, only square matrices, but not just because the matrix is square, that means that it has an inverse. So if we have a matrix, like the previous example, has an inverse, then we say that matrix, it's called invertible or non-singular. So if the matrix does not have an inverse, we call it singular, because it's not invertible. So we refer to them as singular. And I know that, the negation here does not match because we use the word non-singular for invertible. And we could use the word singular for non-invertible. Okay, so think of this, if it's singular, it does not have a multiplicative inverse. It doesn't have a single matrix that the product will give you the identity matrix. So to see this, note that when A is of order m by n, meaning the number of rows and columns is different, and B, okay, so this is A, and B is of order n by m, and again, let's point that out, that m and n are not equal. So the products AB and BA are of different orders, so they cannot be equal to each other. So if we multiply A times B, we have that matrix A is of order m by n. And then matrix B is of order n by m. So remember, to make sure multiplication is possible, we have to verify that the two numbers here in the middle match. The number of columns of A with the number of rows of B. Since that is true, then the product is going to be of order M by M. Now, if we verify with the other direction, B times A, so matrix B is of order N by M, and matrix A is of order M by N. So again, the product is possible, and the dimensions of the product BA will be N by N. And remember, we're saying here they're not equal. So matrix multiplication is non-commutative. However, if the matrix has an inverse, that is one of the special cases that it is true that it is commutative. Okay, so we are going to solve a system actually, not kind of, yes, we're going to solve a system to find the inverse of a matrix. But this is not how we will be finding the inverse with the formula of a 2 by 2, or how we will be doing it for a system that is bigger than a 2 by 2. So this is a formula that we will be using later on. So we will come back to this one. But before that, we're going to solve that first example. Okay, so to find the inverse, which is the question of example 2, what is the inverse of this matrix? So we are going to solve the equation, and we have our variables here. On the first row, we have x11 because it's in the first row, first column. Then we have x12 because it's in the first row, second column. Then we have A21, second row, first column. And we have, sorry, I said A, I meant X. X22 because it's in the second row, second column. So we take the matrix A, the one that we're trying to find the inverse to, and we have that matrix here. So it has the same numbers, 1, 4, -1, -3. So you can see that here, 1, 4, -1, -3. And we want to find the x values because those x values are going to be the ones that will give us the answer to our question. What are the numbers that will go there and place in the first row, first column, first row, second column, second row, first column, and second row, second column. So what will be the numbers that go there so that we can have the inverse of matrix A? So what we're going to do is equal that to the identity matrix, because remember, when I ask you something like, if you have the number, let's say 10, what number do you need to multiply that number by so that you get a 1? And so the answer is 1 over 10. And we know that 1 over 10 is the multiplicative inverse of 10. So that is kind of like the same idea. So we are going to multiply matrix A times X. So we have, and I'm just going to erase a little bit of this. Okay, so we're going to have first row times first column. So that will be 1 times x11, so that's here, plus 4 times x sub 2, 1, so it's 4 times the variable. Then we move on to first row, second column, and we have 1 times x12, so that is here, plus 4 times x sub 2, 2, so 4x sub 2, 2. Now we move on to second row, first column, and that will be negative 1 times x sub 1, 1, so it's negative x sub 1, 1. And then plus negative 3 times x to 1. So because it's a negative 3, we have a minus here, and then 3 times the variable. Then finally, we move on to the second row, second column. So that will be negative 1 times x12, so that is here. And then we have negative 3 times x sub 2, 2, so negative 3x sub 2, 2 instead of the plus. So now the identity, it hasn't changed. We're just transferring that identity matrix down. And so now we have the system of equations that will come from here. 1x sub 1 plus 4x sub 2 is equal to the 1 here, because they have the same location. Then we have here's second row, first column. Here's the equation for second row, first column. Sorry, second row, first column. So it's equal to the entry here, second row, first column. And so that is the number 0. And similarly, we have first row, second column is going to equal 0. And we have that equation here. First row, second column equals 0. And then finally, we have second row, second column is equal to 1. And the equation is here. And so we can see how those two have the same location within the matrix. And that's why we could say that they are equal. So now with these two systems of equations, we're going to solve them. I'm going to use elimination for the first system. So here I can cancel those two out because they have opposite coefficients, 1 and negative 1. And we have to group them so that they have the same variables. Then we have, if we add them, we will have 4 minus 3, so that is a 1. That's a coefficient, 1x sub 2, 1. 1 plus 0 is 1. So the variable x sub 2, 1, meaning second row, first column, is going to be equal to 1. Now, if I take this equation here and I say x sub 1, 1 plus 4 x sub 2, 1 is equal to 1, I can substitute the number that I got on the previous one, this one here. And so we will have x sub 1, 1 plus 4, and then times that numerical value, which is 1. And now we're going to solve for 1. So we get x sub 1, 1 plus 4 is equal to 1. So x sub 1, 1 is equal to 1 minus 4. So x sub 1, 1 is equal to negative 3. And that way we have two of those variables. Now let's find the other two. So you can see how x sub 1, 2 cancels. And then if we combine like terms here, we will get positive 1 x sub 2, 2. So I have another one of the variables. That one is going to be equal to 0 plus 1, which is 1. And now we're going to find the other variable. So I'm going to use this equation. So we have x 1, 2 plus 4 x 2, 2 is equal to 0. And then we're going to substitute that variable with the number that we found here. So x sub 1, 2 plus 4 times 1 equals 0. So x sub 1, 2 plus 4 is equal to 0. So x sub 1, 2 is equal to negative 4. And now we have all four of the variables. And going by their subscript, we have here first row, first column is a negative 3. Then let's find first row, second column is a negative 4. Then we have second row, first column, that will be a 1. And second row, second column, also a 1. So what that means is that we have the matrix that we were looking for, the one here, A inverse is equal to those numbers that we found. I forgot, negative 3, negative 4, 1, 1. And so that will be the answer to the question, what is the inverse of that matrix? Now, we're not going to find the inverse of every matrix that way. It was just an example. You might have a question like that on your homework. And see, we got the answer correct. That's good. So if we were to be asked to check, we could use matrix multiplication. So multiply matrix A by the one we found, matrix A inverse. And we're not going to do that because we already did an example like that, but it does work. We will obtain what we're supposed to, which is the identity matrix. A different way to find the inverse of a matrix is by using the row operations that were used with the Gauss-Jordan elimination or Gaussian elimination to solve a system. And the idea is that you want to find a matrix that when you multiply with another matrix, you will obtain the identity matrix. So if you remember the system of equations that we had something similar to that. So we had the equations, actually I'm going to write the coefficients. Okay, it will be 1, 4, negative 1, and negative 3. And you can see that here, 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 and here. So, and then we had the numbers 1, 0, and 0, 1. So if we take one at a time, that is what we were solving for. In fact, we did it twice. And then we did the second system. So 1, 4, -1, -3, multiply it by the second column of the identity matrix, and whatever we obtain by solving that system, those are the two columns that we have here. -3 and 1, that goes here. And then the second column, -4 and 1, that's what goes here. So if we do that process and we equal that coefficient matrix to not only one column at a time, but the whole identity matrix together, and we simultaneously solve them by combining them. So like it says here, by adjoining the identity matrix to the coefficient matrix. So what we're going to do is apply the Gauss-Jordan elimination. So we have this, we call it a doubly augmented matrix because we are, remember, adding that identity matrix. So we're not just adding an extra column for constants, but we're adding two columns to represent those two constants. So the idea is that after performing the row operations, what we're going to get is identity on the left, and on the right, we're going to have the inverse of the matrix. So that is our goal. So as you can see, we start and we already have the first row, first column with the number 1. Remember, that is our goal, to solve it in that order. So first we want to work on the first column. First column first. You must follow this order. And we need to find that 1. So we already have that. So then we move on to the next step, which will be to make that 0 for the second row, first column. And so we have a -1. So the only way we can make a -1, what we will add to a -1 to get 0 will be a +1. So we could say +1 row 1 plus R2. And that will be, well, first of all, actually, I'm going to move this a little bit because row 1 is going to remain the same. So 1, 4, 1, 0. Then I'm going to have 1 minus 1, or 1 plus -1 is 0. Then 4 plus -3 is 1. And then 1 plus 0 is 1, and 0 plus 1 is 1. But the first row remains the same because it already had the 1, and in fact, it is our leading row. Now that we're done with the first column, we could move to the second column, and the first thing that we do once we're in the second column is make the 1 on the bottom right corner. As you can see, we already have it. There's a 1. So the next step will be to make this this number 4 into a 0. So we ask ourselves the question, what do you need to add to a 4 to turn into a 0? And the answer is the additive inverse, which is -4, or the opposite of 4, -4. And so we use the leading row, and that's why you see here -4 times R2. Now R2 is the leading row, and then we add that to that new row 1. Or not add it, not new, but we add it to row 1, and that's going to give us a new row 1. Okay. So this is actually for the first row. So let's copy the leading row right here. Leading row is R2, and here at the beginning, the leading row was R1. Okay, so now, actually, no, I have this wrong. Okay, so I fixed the notation a little bit. So right here, the leading row was R1, because that was the one that we were using to multiply the other by a constant, and also because it had the leading one right here. And then with the second example, we have the leading row is R2, because that's the one that contains the positive one, the leading one, and that's the one we're multiplying by a constant. So let's go ahead and just copy R2 like it is. We're not going to change anything to it. What we're trying to do is create a new row 1. So if we multiply -4 times row 2, this one, we will get -4 times 0 is 0. Then -4 times 1 is -4. Then -4 times 1, again -4, and -4 times 1, -4. Then we're going to add row 1 from the previous step. So I'm just going to write it here, 1, 4, 1, 0. And if we add those two, we will get 1, 0, -3, and then -4. So this one here is my new row 1. That we're going to write down here, 1, 0, -3, and -4. And so now that we have obtained the identity matrix on this right side, left side, as you can see here, now this matrix here is what forms the inverse of A. And if you remember from last example, we actually got the same matrix by using as two systems of equations. From here, we obtain the same. Okay, so we're going to do one more way to find the inverse of a matrix. With a 2 by 2, that is easier. But if you were to find the inverse of a matrix of a 3 by 3 or bigger, you will have to always use this method, which is by using the Gauss-Jordan elimination to find the inverse of the matrix. So before we get to that formula for only for a 2 by 2, let's just go over some definitions. So let A be a square matrix. Remember, only square matrices have an inverse. So it has the same number of rows as the number of columns. And so the first step is to write down a system that has the same number of rows as we see here, but we double the number of columns, and we double that because we have to include the inverse matrix there. So that's why it says 2n, considering both. Two n columns. Also, if possible, we row reduce A to I using elementary row operations on the entire matrix. So you have to apply the same operation to the whole row. The side on the left side of the dotted line and the right side as well. So we make this A result into the inverse. And what happens is that the inverse, after applying the row operations, will result into the inverse of matrix A, just like we did on our previous example. And so if this is not possible, that means the matrix is not invertible. So you could also check your work by multiplying to see that A times A inverse will give us the identity matrix. Or the other way, A inverse times A equals identity matrix. That is how you will check your work. If you have a graphing calculator, you can do that with your calculator. I will be recording a video on showing you how to find the inverse with the calculator, how to do the Gauss-Jordan elimination, and that is so that you can check your answers on the exam, but you will still need to do some steps in between. Okay, so here the next and last way that we will use to find an inverse of a 2 by 2 is going to be used with found with using the formula, but I want to make this very clear. It's only for a 2 by 2 matrix. So we have matrix A here, and we're going to call the numbers inside. Just to generalize it, we're going to use letters. So we have the number in the first row, first column is A, and the number in the first, the number in the first row, second column is going to be B. Second row, first column is C, and then second row, second column is D. So as you can see here, the main diagonal is A and D. It includes A and D. So the other diagonal, it includes B and C. And what we're going to do is multiply A times D, so the 2 in the main diagonal, and then we're going to subtract the product of B times C. And if that was to equal to 0, then there is no inverse. So the matrix A, so let's say if that product equals to 0, A inverse does not exist. Meaning that matrix A is non-invertible. However, if that product is not equal to 0, as you can see here, if that product is not equal to 0, that means that A is invertible, and therefore there is an inverse. And so the formula for that inverse is going to be whatever number we get here that is not 0. We use the reciprocal of it, that number, you can see it here, so it will be 1 over that number. And by the way, this number here is called the determinant. The determinant. And so If the determinant is 0, that means the matrix doesn't have an inverse. But if it's something other than 0, it does have an inverse. And the next step that we do, so the reciprocal of the determinant is going to be a constant. So this is the 1 over the determinant of A, of matrix A, is a constant. And we're going to multiply that constant. So this is a constant, just a single number. We're going to multiply that times another matrix, and this is where the matrix will come from. We will switch the two entries from the main diagonal, okay? So A and D switch places. And as you can see here. And then the entries for the other diagonal, they're going to keep their place, but we're going to multiply them by 1. So B and C are going to get multiplied by -1 because we want to change the sign to its opposite. So here again we have the AD minus BC is called the determinant. And so this formula only works for a 2 by 2. So let's see if we can find the inverse of the matrices here. For matrix A, first we need to find the determinant. So let's see. Determinant of A is going to be the product of 3 times 2 and then minus the product of -2 times -1. So that number is going to be 6 minus 2, and that is 4. Okay, so we do have an inverse for that one. Let's calculate the determinant of B. So if we multiply 3 times 2 is 6 minus, and then -6 times -1. So here we will get 6 minus -6 times -1 is +6. So 6 minus 6 is 0. So here we could say B does not have an inverse. We could also say that B is not invertible. And also we could say that B is a singular matrix. If that matrix was representing a system of equations, then it will simply be a system with no solution. So let's find the inverse of matrix A. So what we need to find it is the reciprocal of the determinant and then we need to switch places with A and D. So D goes here, A goes here, and then B and C are gonna be multiplied by the opposite sign. And remember that it is the determinant. In fact, I want to write it this way. Well, yeah, let's just leave it like it was. Okay, so next step will be 1 over the determinant is the product of 3 times 2. We already have it. I'm just writing it again. 3 times 2 minus -1 times -2. Okay, so this is going to give us a constant. It's going to be a fraction, and then that constant is going to be multiplied by those numbers. So if we change places with A and D, the 2 goes here, the 3 goes here, and then with B and C, instead of being a -1, now we have a +1. It went from negative to positive. And then with -2, it's going to go to +2. So we just changed the sign to its opposite sign. And then we already know that the product that we're going to get from here, from the determinant, is a 4. We found it earlier, but we're actually multiplying by 1/4. Remember, it's the reciprocal of the determinant. So if we multiply that constant by the matrix 2, 1, 2, 3, we will obtain the matrix 2 over 4, 1 over 4, 2 over 4, and 3 over 4. So I obviously have to simplify. So I'm going to write it here on top. So A inverse is going to be 1/2, 1/4, and then we have here 2/4, so that reduces to 1/2. And then we have 3/4, so that will still be 3/4. And so that will be the inverse of that matrix. So one of the applications of inverse matrices is, like, we started the section by solving an equation, and we use that concept of multiplying by the inverse to find the inverse of a system of equations. And so we do have a system here, and the idea again is that you have the coefficient matrix, the unknown variables matrix, then you have your constants, and you multiply A inverse on both sides, left and right, and so you have this. And if we group A inverse, we get the identity matrix, and this is A inverse times B. So the unknown matrix, or the numbers of the unknown variables, will be found by multiplying the inverse of the coefficient matrix times the constant terms of the system of equations. Okay, so we are going to, I'm going to show you how that will work with the system. So here we have a 3x3 system. You can see we have 3 equations, 1, 2, and 3. And what we're going to do is find the inverse for it. And in fact, I already have it here. Okay. So what we do first from a system is we create 3 matrices. We have matrix A. Matrix A represents the coefficients. Matrix X represents the unknown variables. In this case, we are using X, Y, Z. And then we have matrix B, which represents the constant terms. And so what we want to do is first find the inverse which is listed here. That's the first step. And then once you have that, the way you want to solve the problem is by multiplying that A inverse times the constant matrix. And that is what will give you the solution to the system. So here we have A inverse multiplied by matrix B, which is the one with the constants. And after you do that, you will be finding what matrix X is. And if we write it this way, if you recall, matrix X was representing the variables X, Y, Z. So they will go here, X, Y, and Z. And so this says that, this will say that X equals 4,000. And then the next row says Y equals 4,000. And the third row says Z equals 2,000. Because remember, we have two matrices on each side, or one matrix on each side of the equal sign. So they are both 3-row by 1-column matrices. And we are saying that if the location in the matrix is the same, they are equal. So X equals 4,000, Y also equals 4,000, and then Z equals 2,000. So this is the end of the video.